In this video, we're going to extend our valence shell electron pair repulsion theory ideas to look at not only predicting the molecular shape, but explaining how the molecular shape comes about. So we're going to look at hybridization of atomic orbitals, and there's some canonical examples that I would suggest that any student look at. I guess a big one would be looking at carbon as a central atom. So let's say, for example, we want to explain the hybridization in a CH4 molecule. So a methane molecule, we know that this molecule is tetrahedral. We know that the bond angle is 109.5 degrees. So we know that this bond angle comes right out of VSEPR theory. But how do we explain the bond angle? So I guess the question is, or the problem is, how is 109.5 degrees achieved from p orbitals? Because the carbon is going to use its p orbitals, because they're the valence orbitals of carbon, to bond with the s orbitals of hydrogen. And we know a priori that the p orbitals have a 90-degree bond angle. So how do we go from 90-degree bond angles to 109.5? Okay, so the answer is hybridization. So we look at carbon, so we know that carbon has 6 electrons. So we could say 1s2, 2s2, 2p2. So that's the electron configuration of carbon. And we know that it has, it's got 4 valence electrons. If we just look at the valence electrons, we could write the orbits, or the orbitals, sorry. So we could write 1s, 2s, 2p. We could fill the electrons in here. So using Hund's first rule and Pauli exclusion principle. So Hunt-Pauli, Hunt-Pauli, Hunt, Hunt. So here we've filled in the electrons into the orbitals. But now we need to hybridize. And we know we need 4 identical orbitals because we have a tetrahedron. So this tetrahedron reminds us that we need 4 identical orbitals. And right now that's not what we have. We have 3 identical orbitals, but we need 4. So we're going to hybridize all 4 of these to make 4 identical orbitals. So we're not going to do anything to the 1s, we can just rewrite that. But we're going to take the 2s, we're going to take the 2s, and we're going to take the 2p, combine them all together, so that now they're all the same, and we'll refill these 4 electrons back in using Hund's rule and Pauli exclusion. Now we've mixed in an S with 2 P's, so we mixed in an S, a P, and a P. So we have sp3 hybrids. We've actually got 4 of them. So each one of these orbitals now is a hybrid, and each hybrid is an sp3 hybridized orbital. And if I find my red pen, which I didn't get ahead of time, then I can see that each sp3 hybrid has a vacancy wherein a 1s, so this is a 1s orbital from hydrogen, because we need 4 hydrogen bonds. The 1s from hydrogen can go right in here, etc. And form our 4 covalent bonds. So in short, we had to hybridize, which is basically juicing together these orbitals. And a way to look at this would be to say, if we've got an sp3 hybrid, so we essentially mixed an s and 3 p's, because that's what we did. We mixed an s and 3 p's. So we got an sp3 level of hybridization. We have 4 of them, each box is one of them. We can say that this sp3 hybrid is 25% S and 75% P. So it's important moving forward that we can typically report the percent S character. So we would say 25% S character. And eventually we're going to see a relationship between bond angle and S character. But this is how we would go from the native 90-degree bond angle to our 109.5-degree bond angle in methane. Another canonical molecule to look at hybridization in is the water molecule. So we note here that the central atom is oxygen. We know from BSCPR theory that water is a bent structure and its bond angle is a little bit less than 109.5. And this is because it's an AB2E system. So the central atom here would be oxygen. The 2 B's in this way of representing a generic structure would be H. And the E's are the 2 lone pairs. So we have something like this. And we know that lone pair electron repulsion is greater than bonding electron repulsion, so that these lone pairs effectively squeeze the bond angle a little bit less than the canonical bond angle for a tetrahedron. So it's based on a tetrahedral scaffold, but it's actually a bent structure. So how can hybridization theory explain this? Let's look at the central atom oxygen. So that's 1s2, 2s2, 2p4. That's the electron configuration of oxygen with its 8 electrons, 2, 4, 8. We'll draw the orbital diagram. 1s, 2s, 2p. We'll follow Hund's first rule and Pauli exclusion to fill these orbitals. Hunt, Pauli, Hunt, Pauli, Hunt, 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 Pauli. I need 4 identical bonds for my 4, because it's based on a tetrahedral scaffold. I have 4 electron groups around the central atom. And I need some of them to have bonding electrons and some of them to have lone pair electrons. So I'm going to go ahead and hybridize as I did with methane. So 1s. I've now hybridized the 2s and the 2p again. So I'm going to get 4 lots of sp3 hybrids, where each orbital is an sp3 hybrid. And I'm going to go ahead and fill in my 1, 2, 3, 4, my 6 electrons, following Hund's first rule and Pauli exclusion again. So I have, well, first of all, let's fill that. then Hunt, 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 Pauli, Pauli. So there's my 6 electrons in these sp3 hybrids. And I noticed that these two sp3 hybrids here are completely filled. Well, if I grab my red pen again, which I keep hiding, these would be the lone pairs of our water molecule. And then I've got these partially filled sp3 hybrids. Well, they would have vacancies that would allow my 1s orbital from hydrogen to interact with, which would be the 2 bonding orbitals here. So again, exactly the same hybridization would explain the AB2E2 system, and also we saw previously in this video the AB4 system, which was methane. So whether you have an AB4 system, as we saw with methane, or an AB2E2 system with water, what's important is the number of electron groups. If you have 4 electron groups total, whether it be 4 Bs or 2 Bs and 2 Es, you need sp3 hybridization. So you're going to have 25% S character. Moving on now to a structure like carbon dioxide, we now start to look at how hybridization takes care of multiple bonds. So here we have double bonds. Again, we'll consider the central atom, which is carbon. So carbon has 6 electrons. We know from VSEPR theory that CO2 has a linear structure. We know it has a 180-degree up bond angle. So it's got the presence of double bonds. It's got a 180-degree bond angle. It's an AB2 system. So how can we incorporate that? Okay, let's look at the central atom, carbon. So that's 1s2, 2s2, 2p2. There are 6 electrons for carbon. 2, 4, 6. We'll look at the orbital diagram for that. So 1s2, 2s2, we'll apply the electrons using Hund's rule and Pauli exclusion. Hunt, Pauli, Hunt, Pauli, Hunt, Hunt. I need to hybridize. So when I say I need to hybridize, I just want to remind you that I'm saying I need to because whenever I have p orbitals, I've got this problem of 90-degree bond angles. So I say I need to if that number from VSEPR theory is not 90, and it's never 90. At least it's not. There's a couple of cases where, but it's always 90 with something else. So that's why I'm saying I need to hybridize. So I just want to make that clear. Okay, so we've got we've got double bonds here. So I should probably mention now, and then it'll be on your radar. So I guess we'll do a little aside here. So single, double, triple, these are the types of bonds that you typically see at this level of chemistry. Single covalent bond, double bond. We're going to consider a single bond is a sigma bond. Okay, and we'll see what that means a bit, moving forward. A double bond, which I see here, we're going to consider that that's a sigma plus a pi. So we'll say sigma plus a pi, where we're using the Greek letters S and P. And a triple bond, we're going to say, is a sigma plus a pi plus a pi. So sigma plus pi plus pi. Okay, so keep that in mind. So how can hybridization of atomic orbitals give me sigma and pi bonds? Well, as you might imagine, the origin of sigma is from an s orbital, or something at least that's connected with an s. It's more appearance than origin. And pi is going to originate from a p orbital. So that will be a clue to where we're going to go with this. Okay, so if I need two orbitals, well, first of all, let's see if we can predict this. So when I had 4 electron groups, so I had the methane example, I had B4, AB4, and with the water example, it was AB2, E2, but I still had 4 electron groups. So whenever I had 4, the hybridization was sp3, so S, P, P, P. It's summed to the number of electron groups. Well, now I've got 2 electron groups, so you would correctly identify this as sp. So I just need to hybridize one of the, well, Vs with only one of the p's. So I'm going to get my 1s unhybridized. My 2s and one of the 2p's are hybridized to give me 2 lots of sp hybrids. But then I still have 2 unhybridized p's. Okay. So again, see the connection between that number 2 and how many hybrid orbitals you have. I have B2, so I just have sp. I just have 2 orbitals mixed. Let's go ahead now and fill in the electrons using Hund's rule and Pauli exclusion. So we've got Hunt, Pauli, Hunt, 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 Hunt. Although the hybridized orbitals and the unhybridized p orbitals have slightly different energies, they're close enough that you would, the energy difference is less than the pairing energy would be. So you'd go ahead and just apply Hund's rule, and there's no need for Pauli exclusion here. Okay, so I can see that I've got space in the hybrid orbitals for oxygen. So these are interactions with oxygen that can go in here. But I can also interact with oxygen here. Okay, so there's 4 ways I can interact with oxygen. I can't interact down here because that's full. But I've got 4 vacancies, but notice the vacancies have 2 flavors. I've got the hybrid flavor, if that's your taste, and I've got the unhybridized flavor, if that's your tipple. Okay. The hybridized flavor, these are going to be your sigma bonds. The unhybridized flavor, these are going to be your pi bonds. So overall, the carbon has 2 sigmas and 2 pi's, which is as it should be. Remember, we said here a double bond is a sigma and a pi. So I need a sigma and a pi, a sigma and a pi. So I've got to explain 2 sigmas and 2 pi's, and here I have it. I get the 2 sigmas from the hybridized orbitals, and I get the 2 pi's from the unhybridized orbitals. We can see that sp hybridization is 50% s character. Because S is half of the information in the sp hybrid. let's have a look at the bonding in a nitrogen molecule. So nitrogen, we know, is nitrogen with a triple bond to another nitrogen, and each nitrogen has a lone pair. Okay. So if we look at this, we could have, we don't really have a bond angle, do we? But we could have, for example, we have a triple bond, so we know a triple bond is a mixture of a sigma and two pi's. So I know in this here I need a sigma, a pi, and a pi. So we have no choice but to look at nitrogen with its 7 electrons. So nitrogen is 1s2, 2s2, 2p3. Okay. Again, I've got an issue. I don't have any 90-degree bond angles here, so I need to hybridize. So let's look at the atomic orbitals. One S, 2S, 2P. Hunt, Pauli, Hunt, Pauli, Hunt, Hunt, Hunt. I'm going to hybridize. Now I know I need two pi's, and I know that the pi's are somehow linked with the p orbitals. So how many times do I have to hybridize? Well, in the previous example, I had CO2 and I had a double bond, and I only, well, actually, I'll give you a clue. It's going to be exactly the same, but for a different reason. So it might be less awkward if I show you, rather than try to explain it a priori. So this is going to be two sp hybrids. Let's fill this in using Hunt's rule and Pauli exclusion. So I've got Hunt, Pauli, Hunt, 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 Hunt. I need to add 5, so I've got one more. Okay. Yeah, that looks okay. Okay, so clearly I've got a filled in hybrid here, so that'll be a lone pair. So that takes care of this one. So this is for a nitrogen. If I look here, a nitrogen has a lone pair. So I've accounted for my lone pair in one of the filled hybrids. But now I need to make a sigma and two pi's. Well, I can make a sigma with the other nitrogen here. And I've got my p's that I can make two pi's with. So I can make pi and pi. Again, these will be from the other nitrogen. Pi and pi. So here the nitrogen, and I'd have to do exactly the same type of hybridization for the other nitrogen, because remember, in effect, I have two central atoms here. This is the central atom, and that's the non-central atom with respect to this atom, and then vice versa. I could say this is the central atom with respect to this one. So if I'm just looking at this nitrogen, it's capable of a sigma and two pi's with the other nitrogen, and then I'd have to return the inspection and repeat for the second nitrogen. So here we'd also have sp hybridization, and as we can see, it is 50% S character. So now we've started to look at hybridization of atomic orbitals and why there's a need. So remember, VSEPR theory, valence shell electron pair repulsion theory, that predicts bond angle, but it doesn't explain it. We need hybridization of atomic orbitals from valence bond theory to explain the bond angle. So that's why when you inspect a molecule, you would apply it with VSEPR first and then hybridization second. Let's look at methane, which is the first molecule we looked at. We said it was sp3 hybridized. We can write the condensed structure like this, CH4. We could write the line wedge diagram like this, where the lines are in the plane of the board, the wedge is perspective coming towards you, the dash is perspective going away from you. And this allows us to look at the hybridization scheme as well. So I've got this hybrid orbital. If you imagine carbon is right in the middle, the central atom, we can even write that if we want to. Put the carbon right in the middle. And we've got the bond to hydrogen here. So let's go ahead and look at the 1s orbital of hydrogen. So actually, let's do hydrogen in black. We'll do hydrogen in red. We'll stick with black for carbon. So we've got the interaction of the 1s atomic orbital of hydrogen with one of the sp3 hybrid lobes of carbon. We've also got another hydrogen down here. That's a 1s orbital of hydrogen, another 1s orbital of hydrogen, and then finally right at the back, 1s orbital here. Remember, these are the 4 sp3 hybrid lobes. So this is how you would draw, at least attempt to draw a three-dimensional representation of hybridization. If we look at carbon dioxide, we looked at water next, right? If we look at water, we know that water can be written as a line wedge diagram with its hydrogens thusly, its lone pairs here. If we wanted to draw some kind of hybridization representation, remember that everything here was sp3 hybridized again. So we could have oxygen in the middle. We could have our sp3 hybrids again, just like we did with carbon. So we can label those sp3, 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 sp3. And now we can have hydrogens here, the 1s unhybridized orbital of hydrogen. And then these would just be the lone pairs in these orbitals here. Okay, so this orbital interaction, where the two orbitals meet head-on like this and the wave functions can interact, this would be the sigma bond. So these are the sigma bonds. There's 4 of them here. There's one there. So we've got our 4 sigma bonds where the orbitals overlap directly. And we've got the lone pairs where there's just lone pair electrons in there. So let's proceed to look at CO2. So we know that CO2 is linear. It's got a couple of lone pairs on each oxygen. This is a bit trickier to draw. Doable but tricky, especially with a marker and a whiteboard. But we've got the carbon in the middle, and we said that this was sp hybridized because it was linear. So we can have sp hybrid here, sp hybrid here. So there are hybrid orbitals. But remember we had two original Methane p orbitals that weren't hybridized. So we'll have one up, we'll just call that P. We also have one coming in and out of the board. What's the best way to draw that? I'll probably label this PZ. PZ. So PZ, here I'm taking the z-axis to mean up and down. And we'll have, this would be X, so my other P would be going backwards. We'll call this PY. So here I'm taking the three Cartesian axes to be Z, Y, and X. Okay. So the PY is literally coming out of the board and into the board. The PZ is going up and down, and my hybrids are going in the X direction. So again, it gets kind of tricky to draw with a marker and a whiteboard. But then I've got my oxygen. My oxygen isn't hybridized. Only my carbon's hybridized, right? So that's just got a good old p orbital. Let's say px. So there's a sigma interaction. Here a hybrid sp and an ordinary px atomic orbital, they just meet head on to form a sigma bond. But the p orbitals, there's three p orbitals on oxygen, so I've also got pz, and I've got py, which is this one back here. And if I finish this off and then I'll do the other side, hopefully that will be as clear as I can make it with this information. Okay, so notice I have two parallel pz orbitals. So there's an interaction between the parallel p orbitals So you imagine two parallel p orbitals, so my elbows and my wrists are parallel. So my elbows, imagine my elbows and my wrists are interacting somehow, they're sensing each other's presence. So each one is contributing, that's why I've drawn halfway a black line from the carbon PZ and halfway a red line from the oxygen PZ. So this single parallel interaction is a pi bond. So between these two carbons, we have a single sigma and a single pi. Remember, a double bond is a single sigma and a single pi. So we've just drawn this interaction here, single sigma, single pi. Let's do it again the other side. So to do it again the other side, I'm probably going to have to redraw this somewhere, because that's probably going to get in the way now. Let's at least scooch it over here a bit. Okay, so I have this drawn here. Let's go ahead and repeat it on this side now, which is easier said than done, but we have our px, we have our unhybridized pz, and also our py, which is coming out of the board. Okay. So now you notice that the PZ is already interacted here, so it's not going to interact again. It's got nothing left to interact with. but we haven't done anything with the PY. So the PY is now going to interact behind the scenes over here. And likewise, the PY that's in front here is going to interact. So we have a secondary pi and a sigma here as well. So if we, first of all, notice that if we look at this half now, we've got a sigma and a pi. If we look at this half, we have a sigma and a pi. So we've got both halves of our molecule accounted for. Notice also that the pi bonds are orthogonal to each other. So if I were to look right down the plane of this, right down the bond axis of this structure, it would look like a plus motif where one of the pi bonds is at 90 degrees to the other pi bond. So they're orthogonal, or they're perpendicular to each other. So for example, this pi bond is in the plane of the board, the PZ. But this secondary pi bond, I've drawn it PY. Well, the relationship between the z-axis and the y-axis is 90 degrees. So the pi in the z-axis and the pi in the y-axis are 90 degrees apart. So that's an important aspect. What about the lone pairs? Each oxygen should have 2 lone pairs. Well, that would be accounted for over here by, well, I mean, you can have a look at it. On this oxygen, my PX is being used, my PZ is being used, but what's not being used is the PY. So there's my lone pair. There's my lone pair for the PY. And on this oxygen, and I need the second lone pair, so I can have, well, I should really draw it inside the orbital, shouldn't I? Just hopefully you can see it. So my PY and my PX are available for my lone pairs. And on this side of the structure, again, I'm not using my PZ, so I could have a lone pair here, and I can use what's left of my PX. Okay, so these get pretty complicated when you draw them, but it's a good idea to practice drawing them so that you can interpret them when you see them. Let's proceed to look at the hybridization scheme for N2. So I know I'd have sp3 hybridization again. So I've definitely got a sigma and 2 pi bonds between the 2 nitrogens. So let's go ahead and do our so here's our become a victim to these color codings. Here's our SP. Here's our SP. This is also SP. Oh, here we go. Okay, each nitrogen had 2 sp hybrids. So we go in and we also have 2 unhybridized Ps. So let's call them PZ. And we're already using the X direction, so let's go ahead and use PY. which is supposed to come in and out of the board. Okay, so we've already got our sigma, the direct orbital overlap of two sp hybrids. Let's go ahead and do a pz. That's one of our pi's, but it's both lobes of the pz, so the north lobe and the south lobe, that's 1 pi. So wrists and elbows is one interaction. And then the py, which I'll somehow try and show you connecting behind the scenes. And again, py here. So again, we've got our second pi. Here the pz, which forms the pi bond in the z orbit, in the z-axis, up and down, and then the py's, which form the pi bond in the y-axis, are at 90 degrees from each other. Our lone pair, we need a lone pair on each. Well, that could just be in the sp3 hybrid, this sp hybrid orbital here. And now I'm thinking I might have made a mistake with CO2. I'm going to go back. Rather than reshoot the video and go back and check, I'm going to redo CO2 because I've got a sneaky suspicion. Only time will tell when I finish recording. I'll check the video myself. I've got a funny suspicion I didn't do the other side of the hybridization. So I'll go back and do that right now. So we have the sigma bond, 2 pi's, a lone pair, a lone pair. Sigma bond, 2 pi's, lone pair, lone pair. So I'm going to clear this board and go back and do CO2 to make sure that we did it right. Okay, so just in case I'm messed up with the CO2 and I don't know yet because I haven't been able to look at the video yet because I'm still recording it. Let's just do it again. We said we had sp hybridization, so let's do that. We only hybridized the central atom, so that's carbon. So maybe I didn't make a mistake. If I didn't make a mistake, this is just an unnecessary duplication, but it can't hurt, and it can help if I did make a mistake. Py. Okay, so we've got the third P is tied up with the hybridization. The two other P's are unhybridized, PZ, PY. Okay, so that's P done. Sorry, that's carbon done with its P contingency. Then we've got oxygen, which has its PX. It's PZ. It's PY. So we have a sigma bond from the direct orbital overlap of the sp hybrid from carbon and the unhybridized px from oxygen. Then we have an across space interaction. Again, pi orbitals are both wrist and elbow. That's one interaction of the pz. So that would be 1 pi. And then I've got to do the lone pair. So again, I'm looking at just one of these now. So I've got my carbon and my oxygen, my sigma and my pi from my double bond. But then I need my lone pair. Yeah, now I'm thinking I didn't make a mistake because this looks identical to what I had. Okay. So I can have my 2 lone pair. So now, anyway, I'll continue, but now I'm thinking I didn't make a mistake. Because this is starting to look the same. But we'll continue. I've got my PX, my PZ, my PY. My PZ is already being used, so now I'm going to go for my PY, which is going to be behind here, and again in front here. There's my second pi, and here's my second sigma. Here's my lone pair. So my lone pairs on the PZ and the PX. So now I've done the second one. So I think this is the same as the earlier recording. I don't think I did make a mistake on the first one, but this was just in case. So this will conclude this video looking at some hybridization, some valence bond hybridization, again to explain how we can increase the bond angle by introducing S character. And I guess we should probably summarize what we have. So I'm going to clear this board up and do a summary board. So this will serve as a quick summary of what we've said and more that will be useful moving forward. So here A represents the central atom, B represents the non-central atom, and E represents the lone pair of electrons. So we can see the hybridization needed for these common structures that you might find. So an AB2 system, all we're doing here is we're looking at the number of electron groups. So if I've got 2 electron groups, then I need sp hybridization. Here I've got 3 electron groups. Here I've also got 3 electron groups, so I need sp2 hybridization. In all cases here, I have 4 electron groups, whether it be 3 and 1, 2 and 2, or 4. So here I have sp3 hybridization. In this category here, I always have 5 total. So this would be sp3d. So sppd, there's a 5th one. And in all cases here, I have 6 electron groups. So this would be sp3d2, sppdd. And a way to think of this is you've got 1 s orbital, 3 p orbitals, 5 d orbitals. So if you need 2 electron groups, you've just got 1, 2, so it's sp hybridized. If you've got 3 electron groups, it's sp2 hybridized. A 4th electron group, it's sp3 hybridized. A 5th electron group, you now incorporate a d, sp3d hybridized. And finally a 6th electron group, you've got a 2nd d, sp3d2 hybridized. One final thing I'd mention here, out of the things that we could possibly mention, is the percent S character. So keep in mind that as we add more and more S character, so we can see here, essentially we're diluting S with P's and D's. So as we go down here, we're reducing S character. So we know that the bond angle is proportional to S character. So that's the one final comment that I would make. And I think this will conclude this short video.